Number 1 says, two different points on the line y equals 2 are each exactly 13 units from the point 7, 14. Draw a picture of the situation and then find the coordinates of these points. So if we draw the axes here, and, the line y equals 2 is around here, and that line basically means that for every x value, the y value is 2, which is just a horizontal line, and the point 7, 14 would be around here. And it says that this point, there are 2 points on this line, which you could just draw here, that are both exactly 13 units from the point 7, 14. So we know that this is 13 and this is 13. So if we draw a perpendicular line down here, we know that we'll have a right angle here, and we can use the Pythagorean theorem. And because we know that this line, that these 2 points are both the same distance from this one point, we know that these two sides here of the triangles are equal length. And so, because this is line y equals 2, we know that the length of this line here is 12 if you subtract 14 and 2. And we can just use the Pythagorean theorem here. And if you see the numbers 13 and 12 in a right triangle, then this should ring a bell because it's a perfect triple. But if you haven't memorized them yet, then you can just do it out. This would be 13 squared minus 12 squared equals x squared, which is 169 minus 144 equals x squared. So x squared equals 25, which means x equals 5. So if we know both of these are 5, then we can just subtract 5 and add 5 to 7, because this is the point 7, 2. So this would be 2, 2, and this one would be 12, 2. And those are our 2 coordinates. Number 2 is asking for a point that is the same distance from 3, 0 as it is from 7, 0. Find lots of examples. Describe the configuration of all such points. In particular, how does this configuration relate to the 2 given points? Okay, so if we draw the coordinate axes and the point 3, 0 and 7, 0, it's probably already really obvious that the point that we're looking for is right here, and it would have the coordinates 5, 0. But the way we find that is by averaging the x and y coordinates of the points 3, 0 and 7, 0, because if you average each coordinate, you'll be finding the midpoint distance between each two, which is going to be exactly in the middle of the 2 coordinates. So for the x coordinates, it would be 3 plus 7 over 2, which equals 5. And for the y coordinates, it would be 0 plus 0 over 2, which equals 0, which is why it gives us the point 5, 0. And this one was probably the most obvious one, but if you think about it, every point on this line with the x value of 5 is going to be equidistant from the points 3, 0 and 7, 0. Because let's say we just pick an arbitrary dot and put on the line x equals 5. If we look at it, this 3, 0 is exactly 2 points away from 5, and 7, 0 is also exactly 2 points away. So if we connect it into a triangle, or just the distances, and we decide to use the Pythagorean theorem, they both share 2 as their base, and they both have the same height, which is y. And so if you use the Pythagorean theorem, they're both going to have the third side of the square root of 2 squared plus y squared. And that's what it would be for every single point on this line, because they share the same point here, and they both have base lengths of 2. So the configuration of all of these points would be the line x equals 5. Number 3 is asking us to verify that a hexagon formed by 6 points that they give us is equilateral. And then it asks if it's also equiangular. So let's draw the hexagon, and the 6 points that they give us are a equals 0, 0, b equals 2, 1, c equals 3, 3, d equals 2, 5, e equals 0, 4, e equals 0, 4, and f equals negative 1, 2. So if we draw this hexagon, wow, that's horrible, but it doesn't really matter. Okay, and we want to do this like a fast way, and then we can do it the more mathematical way, but if we just draw the triangles right triangles on each of the side lengths, we'll see that each triangle here has one side length of 2 and one side length of 1, and that's true for every single one, which means that if we use the Pythagorean theorem to solve for the side length, then we'll get the same answer for every single side, which means that this one has to be equilateral. Also, but if you want to do it using the distance formula, which states that the distance equals the square root of x2 minus x1 squared plus this y2 minus y1 squared. And x2, y2 are basically the first set of points that you want to find the distance between, and then x1, y1 is basically the second pair of points. So this point could be x2, y2, and this point could be x1, y1. So basically this could look very similar to the Pythagorean theorem, which states that c equals the square root of a squared plus b squared. And this is because they literally are the same thing. The distance formula and the Pythagorean theorem are essentially the exact same thing, but the distance formula takes into account the distance's position on the graph, which the Pythagorean theorem doesn't. So if we want to prove this for points A and B, then we would just take A, which is the point 0, 0, and B, which is the point 2, 1, and plug it into the distance formula. So we would get D equals x2, which is 2, minus x1, which is 0, squared, plus y1. Oh, also, last thing, it doesn't matter which one you set as y2 or y1, because even if you get like a negative number while you're subtracting them, then you will be squaring it in the end anyway, so it didn't really matter. But you have to make sure that you keep them consistent with each other, like you can't switch the coordinates around. So, this one would be 1 minus 0 squared, which equals the square root of 5. And if we went around and did this for all of them, we would get root 5 for every single one. Okay, so the next part of the question is asking if it's also equiangular. And if we take a look at it, if I drew it better, we would see that it's just not, because the angles don't look the same, and they're not. But the way we could prove this is by just looking at the triangles that we make by drawing them. And if you look at all of the angles, you see that these three angles are all the same because they all consist of 2 times this angle right here. But then the angles here, these three, are different because they consist of this angle here, the small angle of the triangle, plus this middle angle, which I'm assuming is equilateral, but we're not sure. So this means that these three angles are different. That means that the red angles and blue angles are different lengths, or different sizes, which means that it can't be equiangular, because equiangular means that every angle is the same. Number 4 asks, draw a 20 by 20 square ABCD. Mark P on AB so that AP equals 8, Q on BC so that BQ equals 5, R on CD so that CR equals 8, and S on DA so that DS equals 5. Find the lengths of the sides of quadrilateral PQRS. Is there anything special about this quadrilateral? Explain. Okay, so let's draw this square. 20 by 20. And we're going to first label the corners. And it says mark P on AB so that AP equals 8. So it would be somewhere around here. And that's 8. Mark Q on BC so that BQ equals 5. So this would be Q. This would be Q, which is around 5. Mark R on CD so that CR equals 8. And then mark S on DA so that DS equals 5. This is S, and that's 5. And then we're going to draw a quadrilateral and then find the side lengths. Okay, so it seems pretty obvious how we're going to do this. Just use the Pythagorean theorem for every side. So if each side length is 20, and we know this partial side length, then we can easily find this length and this length. So if this is 20 and BQ is 5, then QC equals 15. If S is 5 and RC equals 8, then we know that DRE equals 12. If AD is 20 and SD equals 5, then we know that AS equals 15. And if AB is also 20 and AP is 8, then we know that PB is 12. And what do you know? All of these triangles are the same. Wait, sorry, no, they're not. But these two triangles are the same, and these two triangles are the same. So now we'll just use Pythagorean theorem. So for the green triangles, it would be 12 squared plus 5 squared, square root. And the numbers 12 and 5 should once again ring a bell because they're a perfect triangle, perfect triple. But if you're not sure about that, or you didn't memorize them, then you can just do it. So that would be square root of 144 plus 25, which equals the square root of 169, which equals 13. So each of these side lengths are 13. Now for the 8 and 15 one, let's just do it out. So that's 225, which is 15 squared, plus 64, which is 289. And if you plug that into your calculator or you've just memorized it, that's 17 squared. Sorry, I meant to do that in blue, but probably get it. So these are both 17. And those are our side lengths. And if you look, the opposite sides are both the same length. And all these two both have the same slope. And these two lines both have the same slope, which means that this is a parallelogram. Number 5 says, verify that P equals 1, negative 1 is the same distance from A, which equals 5, 1, as it is from B, which equals negative 1, 3. It is customary to say that P is equidistant from A and B. Find 3 more points that are equidistant from A and B. By the way, to find a point means to find its coordinates. Can 2 points equidistant from A and B be found in every quadrant? So let's just draw the coordinate axes. And point P is at 1, negative 1. Point A is at 5, 1. And point B is at negative 1, 3. So if we draw the distances, okay, we can do this many ways, but I'm just going to use the distance formula, which this is review from a different problem back then, so I can't remember which one it is right now, equals the square root of x1 minus x2 squared plus y1 minus y2 squared. So if we just do it with BP first, we get the distance equals the square root of, well, point B is negative 1, 3, and point P equals 1, negative 1. So this would be x1, which we can just make x1, y1 as b. So that would be negative 1 minus 1 squared plus 3 minus negative 1 squared. And minus equals positive. So the distance equals the square root of 2 squared plus 4 squared, which equals root 20. And if we do it using A and P, and A is 0.51, then we get D equals the square root of 5 minus 1 squared plus 1 minus negative 1 squared, which equals positive. So the distance equals the square root of 4 squared plus 2 squared, which is the same thing as we got here, but I'll erase that now because it goes in the middle of our drawing, which equals square root of 20 again. So we just proved that point P is equidistant from B and A because we calculated the distances and they were the same. If we want to find the 3 more points that are equidistant from A and B, then we just have to find the line through P that for which every point is equidistant. So if P is 1, negative 1, A is 5, 1, and B is negative 1, 3, then if we just find, we know P, which is 1, negative 1. If we just find 1 more point on this line, then we can just use these 2 points to find the equation. So we know that the line that is the midpoint of A and B is also on this line. because it intersects this line at a 90-degree angle, which is how distance is measured. So if we just find the midpoint of A and B, then we have both of our points, and we can find the line. So A is 5, 1, B equals negative 1, 3. So the midpoint would be 5 minus 1 over 2, which equals 2. And 1, 3 minus 1 over 2, which equals 2. So this is the point 2, 2. And now we can just put it into point-slope form, which states that y minus y1 equals m, which is the slope, times x minus x2. I'm sure you've already learned that formula if you're in algebra or you've already passed algebra, but if you haven't, this is basically how you find the equation of any linear formula or any linear two dots as long as you have the 2 points. So y minus y1, which we'll just make this y1, x1. And, wait, sorry, I just realized that in the formula I wrote x minus x2, but it's x minus x1. So this would be y minus negative 1 equals, and the slope is the rise over the run. So basically if we find the rise, which is 3, because it's 2 minus negative 1, and the run, which is 2 minus 1, so this is 1, then it's just rise over run, so m equals 3 over 1, which equals 3. So it would just be 3 times x minus x1, which is x minus 1. So our equation is y plus 1 equals 3x minus 3, if we factor out the 3 to both sides. So that means y equals 3x minus 4, and that's our line. So basically, if we want to find 3 more points that are equidistant from A and B, then all we have to do is plug in any value of x, and we'll get a value of y that's on that line. So let's just say we plug in 0. Then our point will be the point 0, comma, negative 4, which is around here. And it looks like it's on the line. It would be if I drew it better. And let's say we want to plug in 3. Then we would get the point y, well, if x is 3, and y equals 3 times 3 minus 4, then we get 5. And let's say we plug in 4. X would be 4, and y would be 3 times 4 minus 4, which is 12 minus 4, which is 8. And these are our 3 other points. But keep in mind that every point on this line is going to be equidistant from A and B. Okay, so number 7 says, inside of a 5 by 5 square, it is possible to place 4 3 by 4 by 5 triangles so that they do not overlap. Show how. Then explain why you can be sure that it is impossible to squeeze in a 5th triangle of the same size. So if we have a 5 by 5 square and a 3 by 4 by 5 triangle, we know, or you should know by now, that a 3 by 4 by 5 triangle is a right triangle with a hypotenuse of 5. And it seems obvious that we would just put the hypotenuse on the side length that is 5 because it would fit really well there. So let's say that we just put one of the 3 by 4 by 5 triangles here. We put another one here. We put another one here. And the last one goes here. And look, it fits perfectly. And that's how we would do it. And we can be sure that it's impossible to squeeze in another one by using areas. So the area of this square is 5 times 5, which equals 25. And the area of one of these triangles, 3, 4, 5, is going to be the base times the height divided by 2, which is 4 times 3 over 2, which is 6. So if each one of these triangles has an area of 6 and there are 4 of them, that would be 24. So there's only a unit square left in here, the area of 1. And so there's no way that you could fit another triangle with the area of 6 inside of here without it overlapping. Number 9 says, find both points on the line y equals 3 that are 10 units from 2, negative 3. Okay, so let's just draw this. So this is the point 2, negative 3. This is the line y equals 3. And it's 10 units from this line. So we can just set this length is 10 and this length is 10 and complete the right triangle right here. And because this is a line y equals 3, then we know that this whole length is 6 because this is the point 2, negative 3, which makes this the point 2, positive 3. And if you subtract 3 and negative 3, you get 6. So if this side is 10 and this side is 6, then this is another perfect triple, which you should memorize all of them because it comes in handy, but we'll just do the Pythagorean theorem for now. 100 minus 36, and then take the square root, equals the square root of 64, which equals 8. So both of these lengths are 8, and to find these two coordinates, all we have to do is add and subtract 8 from the 2, 3, but we only subtract it and add it from the x-coordinate because we know the y-coordinate is 3 if it's on the line y equals 3. So we would get 2 minus 3, 3. Sorry, that was wrong, very wrong. We would get 2 minus 8, 3, and then 2 plus 8 by 3, which equals negative 6, 3, and 10, 3. And those are our 2 points. Okay, so number 10 says, on a number line, where is 1/2 of p plus q in relation to p and q? Well, if we just place p and q randomly, and we're looking for what 1/2 of p plus q is, which is the same thing as p plus q over 2, this should look familiar because we've used it in our problems before to find the midpoint. So 1/2 of p plus q is going to be the point exactly in the middle of p and q. And we can prove this by just plugging in random points. Let's say p is 0 and q is 6. Then 0 plus 6 divided by 2 is 3. And obviously the distance between this is 3 and the distance between this is 3. But instead of just using a bunch of points to prove it, it should just be obvious because this is the formula for the average, and the average of the two numbers would be the number that's directly in the middle.